Hi, my name is Joanna Klicka, and today I'm going to be going through HW4 Part D. Question 1 states, generate synthetic data for the response of the process GP equals 1.5 over 7s plus 1 cubed times 12s plus 1 squared to a step change input of magnitude 1.2 over 50 time steps of 2.5 time units. Add Gaussian normal distributed noise with standard deviation of 0.05 to the calculated response. So to start, I already have Google Colab pulled up with our template copied. The first thing we're going to do is set out our process. So we are given that GP is equal to 1.5 over 7s plus 1 cubed, 7s plus 1 cubed times 12s plus 1 squared. That, make sure we have all of our parentheses. I'm going to do this to see if it'll show me it. Perfect. Now we know we have that, right? We can do our simulation. So ty is equal to sim gp. Time is lambda t 1.2. Our number of steps is 50, and our size is 2.5. 50 and 2.5, perfect. So this is our clean data, and so now we want to randomize it. So we're going to say that y data is equal to np dot random dot normal, and we are going to enter y, our function, and our standard deviation of 0.05. Now we're ready to plot this, so big equal to make subplots. Big dot add scatter. So x is equal to t, y is equal to y data, and mode is equal to markers, since this is experimental data. And then we are just going to update the layout. Height equals 600. And there we have our experimental data. So we can see that we have some noise going on, but we still have this S shape. Now we are ready to move on to question 2. This states, fit a FOPTD model to the synthetic data in Part D1 by minimizing the sum square error between model and data. This is a nonlinear regression. So you're going to go back over to the code that we had written here. First thing we want to do is define our function for FOPTD. For this, we're going to have time. We're going to have k of tau in theta. Okay. Then returning from this, we want np.where. We want this where t is greater than theta. And here we have our inverse Laplace. So this is k times 1 minus np dot exponent negative t minus theta over tau 0. Perfect. Now the other function that we need to define is for our sum square error. We're going to define the sum square error, and we're going to have a vector here. our vector is going to be made up of Ka, because that's technically what we have here, not just K, tau, and theta. These are the variables that we want to minimize. That's why we have this. And then we are going to return the sum square of this. So with np dot sum, and we want to take our experimental data and compare it to our real data, our simulated data. So we have our experimental data minus FOPTD, and the inputs there are T, Ka, tau, theta, and we want to square this. And now we want to have some initial guesses. So we have v naught equal np dot array, and our guesses are going to be 1.8, 30, and 15. And now we can go ahead and minimize. To do this, we should first import our library. So from scipy.optimize, import minimize. There we go. And so what we want out of this is Ka, tau, and theta. So we're going to say that this is minimize. Then we're going to put our function in, so some square error, our initial guess, and then we're going to do point x because we want the x value. Now we are ready to plot that, so we can just copy paste this, and instead of y data, we want FOPTD, and we have T, Ka, tau, and theta. Yes, and we don't want markers since this is our model. Okay, shift enter. And here we can see that we have successfully fitted the data. Finally, we are ready to move on to question 3. This states, using the fitted parameters in Part D2 in the calculated PI controller parameters by Smith and Coripio, simulate the closed-loop response of the system to a step change in set point. Alright, so we just go back over to our code, and down here we are going to start by setting out our parameters. We have them here in an announcement from Canvas. I just have it here on my iPad, so I don't have to flip back and forth between tabs. First up is PA, which is equal to 0.586, and then PB, which is equal to negative 0.96. Then I have IA, is equal to 1.03, and then IB is equal to negative 0.165. Next, in this scenario, we want to be using K, not KA, like we were in the past. So K is equal to KA divided by 1.2, since that's our step size. Then we can calculate Y, which is given to us here in a little equation. So PA times theta over tau to the PB power. Then it says that Y is equal to K times KC, and what we want from that is KC, so we just rearrange to get that KC is equal to Y over K. Then we have our final equation that we're going to rearrange to get tau I. And this is tau over IA plus IB times theta over tau. Perfect. And now, as far as our process goes, we're going to have GC, which is equal to KC times 1 plus 1 over S times tau I. And then our closed loop is everything in the forward direction, so KC times GC times GP divided by 1 plus everything in the closed system, so that's 1 plus GC times GP. Great, now we can simulate. We are going to have ty underscore servo is equal to sim. We have GCL. Our time, we have lambda t is just 1. For n, we have 1,000, and our step sizes are going to be 0.5. Now we are ready to plot, so we have fig 1 is equal to make subplots. Fig 1 dot add scatter. Here we have x is equal to t, y is equal to y underscore servo, and mode is equal to lines. And then fig 1 dot update layout. Let's have our width at 800 and our height 600. And there we have our response, and we can see that it's about the same as our other plots, where it goes up, overshoots it a little bit, but eventually gets on track and hits our 7.